So I will have 1 over q squared behavior. Well, when q is very small, I should think of the small correction of the mass. But we can also discuss that. The point is when I do that, well, that you're going to do in field theory, what we can show that the bottom line of all these complicated expressions is that when you go from energy E1 to energy E2, or the momentum exchange Q1 to momentum exchange Q2, then basically you get the same physical expression, where the coupling constant that you had here has to be substituted. So the value of the coupling constant actually does depend on the energy or distance, but not the overall behavior. The potential of the photon interaction is going to be 1 over r. That you know on dimensional grounds. You don't even have to do a computation. This is just to sort of reassure you that everything goes right. There is no other, photon is massless. Or better to say, if I assume that it's massless, then of course they can only go as 1 over r. You agree? There is no other scale at a distance r. Just like gravity. I need to introduce some mass. For example, for massive messengers, what would you expect to get? Dimensionally it will be 1 over r, but there must be some sort of indication that the heavier the guy is, the messenger, the less of an effect. And it's a dramatic effect. Okay, if you get to be obese, you basically don't move, and it's exponential. Where this will be the mass of that messenger, let's call it ma, some massive gauge photon. This is a profound result. It has to go under the name of randomization group, and I will comment on that from time to time. And at the end of the course, I actually want to tell you a few words. I'll have to say something about physics beyond the standard model. And one of the most interesting ones is so-called grand unification, where you use this coupling constant evolution to imagine physics at high energies. So the impact of this, what you are saying, these diagrams, that when I look at the potential, it will not be E squared, it will be E squared of that distance, okay, but don't worry about that. I just want to get the form. E squared depends on distance, or alpha, depends on energy. We call it running. Actually, it should be called crawling because the change is logarithmic. You know, just like a baby that barely moves. It's a tiny effect, and it took a lot of energy to find it. You can imagine, when it's logarithmic, you have to move to pretty high energies. But you've heard, okay, this will touch on the issues of scaling and so on. I was talking to Alexei, who is here this week. He told me he did talk about the deep inelastic scattering and scaling and QCD, because he had to sort of, he told some discoveries, because he told me that he told you about how we see the quarks, how even we saw gluons with these jets and so on. I'll remind you along the way, but I'll also assume that you have some notion. We can discuss this more, but let me go on now with my lecture. Okay? Just imagine here some blob. The overall behavior will be given by the measured argument. But what I was talking about is just the classical result, the leading expression, so don't worry about the sophisticated corrections, okay? I was gonna, last night somehow I changed my mind. I stayed up late, this is why I was a little late. I decided that maybe I'll do a little different this year, that I'm gonna hit you, I'm gonna introduce the standard model as soon as possible so that I wet your mouse, and then we go slowly, understand it deeper, and build the sort of road that takes you to a normalizable theory, this spontaneous symmetry break. Because I just thought you had already a W homework. We can even do the ZDK, and I can bring you at the front and then help you grind it. You've done Yang-Mills? Or I will have to do that? Non-abelian gauge series? You know something about non-abelian gauge series? At least the mathematical structure. I don't care about deep physics. But let's see, as I go along, I'll ask you questions and you will help me to see how much I will have to cover of that. So let's start. Oh, I guess it's flush. So let me build the standard model. Let me show you that. I don't know if I'll succeed today. We can always postpone it for Monday, okay? We said that if W were to exist, its form would have to be the one I gave you. The weak interaction Lagrangian we said the other day would have to be some coupling constant. Allow me to normalize it in this fashion. And then an up quark would change into a down quark, or better to say, enters a down quark, comes out an up quark. That's neutron decay. It's not the neutron that decays, it's a down quark that decays. Right? After all, neutron is UDD and proton is UUD. All that happens in neutron decay is D becoming U. This is called N decay. Well, I have to get electrons and neutrinos outside. So this is the form. And we decided it had to be purely left-handed or right-handed. I call it left because parity is maximally broken, we were told by Madame Wu. Notice how we had to say Madame Wu in those days. There were so few women, you had to emphasize it. That he was a woman. You say any netter always, right? Normally you don't say the name, you don't say David Hilbert, you say Hilbert, whatever. Riemann. So let's go back to the 1956. As I told you, it was a special year. Neutrino was confirmed. Well, let's go to 1957. Neutrino was confirmed by that time, and the effective form of ink interactions was determined to be left-handed. Okay, this would correspond to the effective Fermi theory. Which we write up quark comes out, electron comes out. This is a typical effective interaction that describes, say, this would be the Fermi interaction. There is a factor of 4 here the way I've written it. Sometimes there is no factor of 4, but then you just write 1 plus or 1 minus gamma phi. Remember, L has a half in the definition. The half is important to keep it being projector, right? L square is L. These are our projectors. And of course, R goes with a minus sign. So this you knew in 1957. And you know, of course, if W existed, you would have to have that form. When I exchange the W, we can as well say it now. Actually, why don't we convince you? From the modern perspective, if I believe there is a W, how would the interaction look like? Down quark comes, you agree? Becomes an up quark, emits what? Emits a W minus. This is negative charge, this is positive charge. So what is coming out is W minus, you agree? What is coming out in this process is the electron, so I have a correct propagation of charge. Neutrino coming in, according to Feynman, is anti-neutrino coming out.
Yeah.
So
there we have mu coupled to something like gamma mu down, maybe the first one.
oh, it will be better. Thank you.
And is it UD or NB?
Well, it's MP really. I'm writing in a modern language. You're right. In 1957, there were no quarks.
Yeah.
You have some idea when the idea of quarks was introduced? A history, I know, why would you care at your age? You're saying 66. Yeah, it was later, well, 64. And who is the father of quarks? Just Gell-Mann? It's very funny how history treats people. It's true that Gell-Mann wrote a paper on that, a physical letter paper. And he was a professor at Caltech. There was a graduate student at Caltech, Zweig, who took them much more seriously than Gell-Mann. He wrote a series of papers, you should read it. He had problems actually even issuing a preprint. After that, he went to be a postdoc at CERN. And the director of CERN, Van Ho, was a friend of Gell-Mann. And Gell-Mann started to feel that these are mathematical entities, very useful to do the bookkeeping of these funny meson, octets, and decuplets, and so on. But they shouldn't be taken seriously physically. So Zweig even had problems publishing, okay? So, you know, when we teach you, we often talk about Nobel Prizes, okay? I don't like to mention them. I like to mention the prizes that should be given. This drives me crazy, okay? I'm trying to actually encourage. I've talked to some people. I'm not important enough, you know? There has to be a Nobel Prize winner who will push for that. Not only Zweig didn't get a Nobel Prize, but Kobayashi and Maskawa got a Nobel Prize for suggesting fifths and sixth quarks, and the real father of quarks never got a prize, and this is the crux of our issue. By the way, who took the quarks seriously afterwards and a father of scaling and told the experimentalists how to look for them? Alexei should have mentioned, they probably did. Bjorken, another, they're both getting old, and I hope that this is corrected, okay? I'll come back. This is one of the most beautiful papers of phenomenology I've ever seen, the Bjorken's idea how to look for quarks. Remember, you can't really see a quark directly by isolating it. You have to be smart to know how to look for, when you scatter an electron and a proton, for kind of behavior will tell you that there is actually quark inside. Sorry for this side remark. So this is 64. Roughly. 1957, I agree with you, this was neutron becoming a proton, but I'll speak from a modern language. Okay, I can't just do history. I will introduce history for you to see how the ideas evolved, of course. But I need to follow the rigor and the logic of modern particle physics. So look, so how does this process go? Well, it goes through the propagation of the, at every vertex there is a g square over square root of 2. And then, of course, I write UL gamma mu dl and EL gamma nu L. Why don't I erase this? We'll talk a lot about Zweig and Bjorken and Gell-Mann. And then I need a propagator for the W, right? This is what Feynman taught you. So you would put a propagator here for me. There will be factors of Y. Let's not worry about that. I'm just looking at the effective interaction as defined as the absolute value in this point. So what I have is G mu nu minus, let's call this Q exchange momentum, Q mu over MW square, you agree? I will try to keep capitals for gauge bosons masses, Q square minus MW square, something like this. Up to sign. I don't worry about the sign, I don't worry about the factors of Y. Okay. You agree? This is going to be the effective interaction. By the way, you know the value of GF roughly? It's a dimensionful number, of course, because this is a full fermion interaction, right? This is not a fundamental interaction, the Lagrangian. You know how to count the degrees. The mass, you know, dimensions, you know. The dimension of a spinor field is 3/2. We can do that from the kinetic energy. So what is the dimension of this interaction? 3 and 3 is 6. So this has to be some kind of 1 over m squared, and GF turns out to be 10 to the minus 5 roughly. I use the unit as most people do, the natural units of proton mass, the GeV.
I will just invert the mass of the boson, let's say.
Yeah, it's going to be the Lewis mass of the boson, and it's sort of interesting, okay? I'm glad you asked that. Let's see, before we go on. It should be so saying, well, why am I writing in GeV? At that time, Fermi didn't want to speak of the W boson, it would be too speculative as a serious physicist. He wanted to speak in the language that could be proved by experiment. It was unimaginable that you could prove the W boson. You expected W boson to be heavy, we'll see immediately why. Now, which term is going to dominate here? Neutron decay, Q is very small. And other experiments at that time, of course, were done at low energies, okay? This is before the accelerator, big accelerator physics. So Q was basically zero. Notice the thing. Look, imagine that you have a photon here, then W would be, MA would be zero, and the Q would determine the strength of the interaction we just said on the measured grounds. If Q is very small, in some sense the interaction could be strong. Small compared, say, to GeV. Here it's the other way around. Weak interactions, this is the first glimpse in what we know today, are not weak at all. It's just that the messenger is heavy, so it sort of makes the actual effect weaker at that energy. Okay? If you boost a heavy person enough, even the heavy person will, take a big car and give it enough momentum and it will move. So I can take Q going to zero. So notice this ugly piece that would complicate my life, that I wouldn't know how to deal with, doesn't contribute. Life gets very simple, so I get G squared over 4 mW squared. Why 4? Why not I say 2? This interaction, Fermi. And here is Maximum's question, GF over 4 square of 2 is G squared over 2 mW squared. So yes, strictly speaking, it is mW, or let's write the famous interaction GF over square root of 2, let me write it the same way, is G squared over 8 mW squared. So you see how dimensionful arguments are sort of nice. They give you a glimpse of what is going on, but they can be a little misleading. Because I could have said, oh, what is going to enter is mW. No, it's 8 times mW squared. See, dimensionful arguments can fail. Imagine that 8 becomes 100. Then, of course, my naive argument would be even worse. And G may be small. I don't know what G is. So from here, I cannot tell you what mW is. We know today what G is because we know mW or vice versa. Okay. But I knew that I could reproduce this nicely with the existence of some heavy W boson. I could have said to myself, if G is not terribly small, then maybe if W is not terribly heavy. Or terribly light, sorry. If G is not very big, MW will not be. So I may say the following. If the theory is perturbative, then G cannot be large. Large G. So I may be lucky that I can start dreaming. At that time you can even imagine, maybe I should start talking about that, maybe. Anyway, it was established from the study of all the weak interaction experiments that the form was this. This was a great work of Marshak and Sudarshan. There's a beautiful review in recent years, I can send you a copy, by Weinberg. It says V minus A was the key. It was Sudarshan's birthday, I think, fest, and Weinberg spoke how for all of them there was a fundamental input to go on and be able to build a theory. You knew you had to know the form of this interaction. It was suggested independently by Feynman and Gell-Mann, some kind of elegance argument. It would be nice if it was just 2 components, it selects 2 components, but actually Marshak and Sudarshan, independently and even earlier, analyzed all the experiments and had the courage to say that some experiments are wrong. We didn't agree. So, this would be Modern Language 1957, and we are back in time, and let's imagine there are quarks. I can talk of proton and neutron, but why complicate my life, your life? So you and I want to build You're saying the following, you're saying, look, QED works so beautifully. And you knew at the time that the gauge principle played an important role. Okay, the great work of Feynman, Schwinger, Tomonaga, and Dyson, culminating it, shows that it's a good theory to all orders in perturbation. Dyson completes the ideas for these guys. And he shows, well, as they showed before, that the gauge symmetry is fundamental gauge principle. So you say, I want to do the same. Schwinger tried in 1957. Schwinger, besides being a great physicist, he was an advisor to Glashow, which would be very important. Okay. So what should I do? What would be the minimal gauge structure that I must take in order to unify them?
Yeah, why do you look for gauge structure?
Because it worked. Well, I would do the thing. Okay, why did they look? I can pretend that, oh, why do I look? Okay, I didn't do that. I wish I had done something like this in my life. So you may say, well, you may ask, is it a touch of a genius? Could I try to understand why people did what they did, right? In case of Einstein, if you think of general theory of relativity, it would be hard to think why Einstein did what he did, right? That was, that Pauli had a great sense of humor. I don't know if you know that. Very dry. He was a tough guy. He was famous for that. And once there were a bunch of his students and postdocs, they were reading a paper of Einstein. Einstein got old by that time. And young people often feel, at the peak of their achievements, important. And they were criticizing this work of Einstein. Like, it's not very good. And Pauli said, well, stop. Einstein is not completely stupid, okay? So I'm going to use this euphemism. Okay, Einstein was not completely stupid. I would like to say neither was Schwinger or Feynman, but I want to say even you and I, let's imagine that we are completely stupid. I think this would be a natural thing to do. I don't think this is a touch of a genius. If a gauge theory works, do it for the next phenomenon that appears to you. If tomorrow, look, I've been working on trying to understand the origin of neutrino mass most of my life, keep coming back, in the early 70s. I can say proudly it's at the time when people told me the neutrino was massless. The thing that I did was, to me, obvious. There is still no proof that I'm right, and people like me. Take the standard model that worked and try to imitate it for the new theory. That's what you do, surely, if you're not a genius. Actually, the ideas on which I based my work was the seed idea was given by Salam. Salam was not completely stupid. Okay, but he, for example, followed the natural path, which I want to argue follows Schwinger, okay? You will see me from time to time, besides just worrying about derivations, or giving you the logic of, I want you to give the feel, and I will spend some time on that, for how the theories may and should be built. This is normally not taught. You agree that's the reason I'm going to start? Did I reassure you? I mean, QED, I was a peak of its success. Comes a new phenomenon. But that's what you do in life. Pay attention how you understand phenomena. Every time you have an understanding, actually, you will see that you reduce it to the experience of yesterday. Then you feel good. Oh, I understood yesterday, whatever you did. And the day after you will wake up and you will try to use that understanding to explain a new phenomenon.
But I was trying to ask, of course this is a natural way to go, but could it be possible to explain those local interactions without the gauge theory, just a massive?
I don't know. It's a hypothetical question, okay? The answer, of course, is no. Not successfully, because this is the way nature looks like. So there is no other explanation. The beauty of theories of nature means that you have eliminated other theories of nature. It's not that there are other 2, 3 theories that can give you the same result. Okay, there's just Newton theory of gravity and not the competitive theory disappeared. Okay, this is how you choose a theory, by the way. It's a statistical analysis in which you slowly eliminate the other explanations. Okay, in principle, yes. In practice, no. But why would you think of something that is very... Look, when you do that, and people do that, you will go for seminars and now and start to do research, and you will constantly run into people who tell you, now is the time to, you know, change the way the things are done. I don't want to play chess with the rules. Let's change the rules. I don't understand that. Then you're asking me, why do I try to imagine something that you and I cannot imagine? You don't know what it is, and let's speak about that, because you prefer not to. That's anti-understanding. I insist on this. We should follow always, before we fail, what worked yesterday. And I'm surely going to do that for the rest of I will see when I go beyond the standard model. I will have to go beyond the standard model. As we know, neutrino is massive. So I have to incorporate that into the course. So, once again, I want to have a gauge series because it worked. What should be the, you know, how do I build a new theory? I look at the minimal structure that follows a certain principal symmetry idea. That's how Einstein beat gravity, that's how Maxwell beat electromagnetism. Anything you look in the past, only the minimal version can be predicted. You're learning gravity now, right? You're writing the simplest Lagrangian just as a QED that respects the principles that Einstein followed. The simplest action, just you don't square R's, you know, pattern, you know that. So what could be, once again, the minimal group? How should I follow? I'm saying that I want to, on top of weak interaction, I also have the electromagnetic interactions, which is E psi bar gamma mu. This I can write universally, right? I don't have to specify the fermion. All I have to put here, the charge operator, it selects properly the fermion in question. So here maybe we are probing for the first time your knowledge of, that you say you have some glimpse into Yang-Mills non-abelian gauge series. What is the characteristic of QED? The gauge boson accompanies the generator of the, in the case of QED, let's write on the side, psi goes into E, Q, let's say alpha of x, psi of x, right? Q, as we say, is the generator of this U1 transformation.
At that time, let's say that time, did they know that we have three gauge boson, like W plus minus and Z boson, or?
Forget the Z boson, I'm just trying to unify. I just said very clear, I'm very modest here, I want to unify weak and electromagnetic. Of course they didn't know that there was a gauge boson. When was W discovered? Roughly? It's funny, you know how they... Sorry, the dates that are so important to me, I appreciate that. Okay. Roughly. Yes. Much later. 83, 84. 83 is the first moment when these two experiments, Rubia 1 and De La Negra and others, Duroula, actually, the French physicist who was running UA2, announced, first it was UA1 experiment run by Rubia and others, and then UA2 will start to seeing first W. So it's going to be another 30 years. I'm saying, let's imagine you and I. And this is what the standard model was. You never knew. At any point in the standard model, you never knew what the situation was. Standard model always anticipated experiment.
But what I mean, not experimental, theoretically.
What do you mean? You cannot know theoretically. You suggest something.
Yeah.
So that's what I've written. I'm suggesting that there is a double loop. I'm confused by your question. If I write interaction, I'm pretending that I believe that there is a W. I'm saying 1957, once again, I'm Schwinger, I'm saying QED work, QED is a theory based on the gauge principle with a messenger which is called the photon. I'm going to assume that there are similar messengers for the weak interactions, and I call them W and Z, okay? Sorry, no, it's W plus and W minus, no Z.
No.
I don't want to talk about the Z because I have no idea that there should be a new interaction. All I want to do at that time, explain the known interactions, okay? Which is the right way to approach the situation at the time. So, you see, we said that the gauge principle has an automatic incorporation of gauge bosons. When you write, this is coming from the covariant derivative, right? What I did, how did I develop QED? If I want now to take the gauge principle seriously, I can just write the Dirac-Lagrangian and ask that the Dirac-Lagrangian possesses a gauge invariant. Suppose that I do that, go from here to here, I will find out immediately that d mu must be changed into a covariant derivative. I'm asking this to be a covariant derivative so that it remains to be invariant under the transformation. It tells me that a mu transforms is a mu minus 1 over e d mu alpha of x. This is equivalent. When phi transforms like this, a mu transforms like this. So this is the beauty of the gauge principle, okay? If you wish, the form of interaction that I wrote gives you the gauge symmetry, but if you believe in a gauge symmetry, you can fix the form of the interaction. The U1 gauge symmetry gave us the minimal form of the electromagnetic quantum theory. This is U1. QED is based on U1. Non-abelian would be the following. I'll let you answer. What would be the non-abelian generalization? Some SUN. Let's talk about SUN group for simplicity. After all, the standard model, as you know, is SUN. SU3 for strong, you knew that. SU2 for weak, okay? We want to get there. So in SUN, what you would say that psi transforms as e to the, well, let's say some u psi, so that u dagger u is u dagger is 1, and determinant u is 1. And that means that u can be written as e to the IH, where h is Hermitian. And if it is Hermitian and traceless, because determinant u is 1, this you know in your sleep, this is how SU2 is developed. That means that H is sum over TA, the generators. I can expand it in the basis of traceless Hermitian generators. We call them the generators of the group. Q was for U1. For SU2 there will be 3 of them, Pauli matrices. For SU3 there would be, for SU4, 15, for SU5 say,
24.
Let's imagine 24, it's interesting SU5. And there will be associated Euler angles that I can call thetas or alpha. And if it's a gauge symmetry, this will be a function of x. You agree? This will be the generalization of U1. This is what I ask you. You know this, right? To some degree, you know. This is what we call the Young-Mills. Now we have to write down the covariant derivative and so on. I'll write that. But maybe Mahmoud had a question.
No, I think it's resolved, because my question was, is it necessary to know that we have 3 messengers for the weak interaction to relate it to SU2?
Well, we didn't yet say SU2. You want to say, I ask. Or you want to answer my question. No, not ask me. You're answering my question. I ask, what is the minimal structure that can give me weak interaction? You're trying to answer. You believe it's SU2. Well, SU2 has 3 generators. I have 3 gauge bosons, so obviously the smallest one will be SU2. I'm going to try that, Nicolas.
But that time they kind of start forming these doublets between N and P or something like that. Like
Well, that's what we have to do.
so
Well, that's the same thing. That's the same thing. Yes, that's a good point. But I will do that on the. Once I decide it SU2, I will be taken to the doublet picture precisely. Okay, most of you are saying the same thing from the different point of view. But the first, I think, what Mahmoud said I like. If I have three let me start with that. I'm imagining three messengers. Three messengers. That means three generators. Okay. In the case of photon, there was one generator. So why don't I start with a simple such theory, minimal 1 SU2. And we will always follow that principle, okay? I start the minimal. If it fails, I don't know. I may give up. I go home. Well, obviously, I won't do that. This will fail. Let's see the moment, okay?
The minimal one is actually, if you really build an analogous theory, would be the U1 symmetry for the weak interaction too. So it should not work maybe because of.
Good question. Could U1 work? Well, I don't know if that would be minimal. You could have like U1 for okay, an interesting suggestion. I'm glad you mentioned it. Important. I would think you better to comment on that, but it's better there is a question. You're saying, well, photon was U1. Could the W be another U1? Could it? What is the characteristic of U1 by definition? Well, it's a tautology, so I'm sorry. It's a billion. There is just one generator, so it commutes with itself. Which means that the interaction will always take the particle to the same particle. It's just a change of phase. So what the messenger does here is sort of very mild. It lets be emitted, but very gently. Right? It's no, if it's Kevin emitting this messenger, well, he's neutral, presumably, then he remains Kevin. That's not what the double boson does. You see, but we say that photon is neutral. We knew that from the form. Photon has to be neutral. The charge will be violated if photon is not neutral. It may be violated, but remember, we are believing in a symmetry. I believe the charge is a good symmetry. One day I may learn that it's not. That would be a disaster. I wouldn't know even how to form QED. I can tell you a little bit later about that. Fortunately, there are strong indications that charge is a good symmetry, it is conserved. Therefore, we will follow the principle of symmetry. We are now doing something interesting. The interaction had a symmetry. That we loved. We are now playing a dangerous game, of course. We may fail. We are saying, well, if it worked, let me try once again. Let me try the symmetry being the Gaussian principle and see where it takes me. So in the case of SU2, which I will assume here, there are three such generators, and the structure constants are, this is SU2, the thing that I've written there. Right? That means that the ordinary derivative has to become a covariant derivative. Just like in the case of U1, it has the corresponding complex constant, I call it G, and it has three now generators and three gauge bosons associated with that. What is the minimalization of SU2? Minimal representation. There is a minimal gauge group, and then there are minimal representations of a group. Non-trivial, of course, there is a singlet, but it's trivial, that doesn't transform. The first non-trivial one is spin a half, analogy of spin a half. This is not a spin anymore, but sometimes if you hear me say spin, forgive me, I mean weak spin, if you wish, some other. Sometimes we call isospin, weak isospin, and so on, okay? We can use this language, but I may be cavalier and just say spin, okay? That you should understand it from the context, okay? So, in the TA mini, the leading, the smallest representation, this was the minimal group.
The first one is it. So the first one, there is also ordinary derivative. The first term, when we.
Sorry.
SU2.
Yes.
It says ordinary derivative.
The first one.
Capital V should be
Oh,
ordinary also.
thank you. See how reasonable I am. You tell me, I correct it. I've never picked a fight yet. Maybe thanks. It's good that you are. Notice I'm not looking into the notes. I try to do that. Okay. I think it helps that you guys are awake. I'll even try to do derivations without looking into my notes. So I really need you to be careful because I can easily make obvious silly mistakes. So TA, the minimal group would be in the minimal representation. Again, see, we have following minimality. That's a fundamental principle. I'm going to try to do that. Always. Is Pauli. Okay. Which is what Nicolas said. That means that the underlying structure is a doublet. That's the same thing as saying that you are taking Pauli matrices as a generator. So in other words, in this case, psi is some up and down. By the way, this notation I can use for SU2. I don't mean just up and down core. Any doublet in SU2, we should use this name. For example, up may stay for neutrino and electron. In SU2, there is just one upper component and one lower. Spin up, spin down, if you wish. There are many notations. I could use this notation. I could use this notation. Look, psi up. This would be more correct than up and down because this looks like up and down core. That's what I mean by this, or I mean this. Okay. They're all equivalent. And when I say that something is a doublet, I mean that psi transforms as u psi, as I wrote there, where u is e to the I. Well, sometimes I write theta A, sometimes alpha A. I think I more often write theta A in my notes. So don't worry if there is a change. TA. So this basis that I said is true in general. After all, what are Pauli matrices? They are a complete set of traceless Hermitian matrices. Any 2 times 2 Hermitian traceless matrix can be expanded. In SU5, the same way. There will be just 24 of such. And by the way, what I want you, and I will be doing that from time to time, I want you to know SU2 in your fingers. You have to know everything about SU2. Group theory is knowing SU2. I get often students who know sophisticated things like thinking diagrams by knowing what you need. That comes later. It's no SU2. With SU2, you can build anything. Lorentz group, you can build SU5, SU10. It's just putting Pauli matrices in proper places. That's how you build. That's how you get a working knowledge of group theory. I'll be insisting on that. I can assume that this you know more or less, you knew, or now we reminded you and so on. So let's try to see what we get. You can still ask it. Well, I'm erasing. Okay, this I can erase, this you know. We don't need SUN at the moment, we'll come back to that. I just wanted to tell you that once you accept the principle of just generator gauge boson, it's very easy to build any gauge group, Yang-Mills Lagrangian. That's the beauty of the great work of Yang and Mills. And actually show, it's strange how name disappear. At the same time when Yang and Mills wrote their work, Shaw was a student of Salam. And Salam didn't encourage him enough to publish it. He had the same thing in his thesis, amazingly enough. Imagine a PhD thesis which had one of the greatest developments in modern physics, unpublished. So we call it Yang-Mills, it should be Shaw Yang-Mills.
And there in the covariant derivative, just to not confuse, we should call the vector field W? Or
Oh, I'm gonna come to that. I don't know what W is.
we're not going?
We have to derive that now. We should now start from this structure and see that I can actually reproduce weak interactions. I was sort of inspired, I was motivated by the possibility that there is a gauge theory. I said SU2 must be the minimal, now I want to go and check it. Now I'll do the opposite. I will just assume a formal SU2 structure. Tomorrow, you imagine I want to maybe do SU5. And I want us to do together. So let's say, let's take it seriously. Let's forget the motivation. Let's see what we get. It's more fun. I can erase this.
In this theory, we deal with a massive boson, which didn't have the gauge symmetry.
That's an interesting question. I'm going to face the dilemma. I'll come back to that. What shall I do about the mass? That's going to be the question. Very good. Let me not worry about the mass. I just want to reproduce the interaction, then I'll come back to the issue of mass. In order to understand mass, I'll have to teach you, we have to spend some weeks understanding the so-called spontaneous symmetry rate. That's going to become, it's interesting. The standard model, and it's amazing this evolution, started as a modest attempt just to understand weak interactions. It turned out first into discovery of other interactions like neutral currents, but more importantly into the question of the origin of mass, which is a deep, profound, and beautiful question, and it became more that. Today, and you and I will spend more time than previous generations talking about the Higgs, because they are probing Higgs as we speak. So in other words, how will my interaction look like, SU2? There will be some psi, which is a doublet. I wrote it here. Psi bar, gamma mu, I, d mu psi. Everything should come from here. There are, of course, kinetic energies for gauge bosons, Young-Mills ones, okay? Let's not worry about that at the moment. That we will study, but not now. So what is this? This is I. There is psi bar. There is a kinetic energy. That's okay. That's just there. Minus I plus I. I get G, psi bar, gamma mu, A mu A. And I have Pauli matrices. Let me be specific here. That's what I have, right? This is just the kinetic energy. So let me not worry about that. I want to continue with the interaction. Or maybe one does the alpha interaction. Lagrangian of SU2 is this, which is alpha kinetic plus alpha interaction. I'm sorry. Of course, the covariant derivative now must of course carry the kinetic energy. Yes?
Covariant derivative also implicitly has the U1 gauge, but we don't write it there.
Oh yeah, no, it's explicitly there. It's there. I have to see whether I get it. What I have to now show that I get W plus, W minus and the photon.
It's inside of this term.
They better be. I'm very ambitious now. I want to have a complete theory. At that time, there were just weak interactions and electromagnetic ones, and I want to find the unified theory. Like to dream of Einstein to find the unified theory of gravitational and electromagnetic. Now, we knew that Einstein was wrong completely. It's not surprising that he couldn't do anything for so many years. He didn't know which interactions were unified. You can't jump into electromagnetic and gravitational because they are weak that come before, much before the gravitational one, and this is the route to take. Okay, we are better there. And he was not completely stupid. I mean, these days you will hear a lot of everybody wanting to build some profound unifying interactions. I'm very worried. I've worked on grand unification. I was always worried about myself. It's okay when Einstein wants to do that, who has already done some unbelievably profound work. But you know, when we claim that we want to do that, we should think a little bit about who we are and why we want to do it. So what's the interaction? So I have two pieces, psi bar, gamma mu. I can write A mu 3. And let me put T3. I don't even have to write sigma 3 over 2. Let me keep it there. I will separate that. Just, it's universal, so I don't have to specify the form. You agree? It's not changing a particle into a particle. This is typical of a neutral gauge boson. Okay? This is our convention. I can always choose one Pauli matrix diagonal, and that behaves similar to a photon. Because the rank of SU2 is 1. Okay? Rank, what is rank of a group? Number of mutually commuting generators, Cartan subalgebra. And that's just T3. So let's go on. So there is G psi bar, gamma mu. Aha, now we have, these two are off diagonal, so this is 0, A mu 1 minus A mu 2, I. Right? You know Pauli matrices in your sleep. A mu 1 plus I A mu 2, 0. This I have to write explicitly because they are diagonal. And by the way, I should be careful. Why don't I write immediately? U bar, D bar, gamma mu. Let me focus on this piece here. I'll come back to that. Okay, I'm following this. What do I get here? I get G over square root of 2 U bar. There will be one piece when I pick up down here. It's going to couple to U. Right? First we come to first, which will be U bar, gamma mu, D, A1 minus IA2 mu over square root of 2. Let me see if everybody agrees with me. No, you can't agree with me because I missed the half. There was a half here. Pauli matrices come with a half into the generator. Where is it? TA sigma A over 2. I forgot the half, which I wrote in a funny way. I am sort of crazy. I write half is the square root of 2 times square root of 2, okay? But then I may not be completely stupid either. Not at the level of these guys. So there's a reason, okay? Why did I write the square root of 2 here? Please tell me. I want to normalize this state. I start with some states which are normalized. If A1 and A2 are normalized in some way, then I have to put a square root of 2 to keep that normalization. So let's try to keep that normalization. Mahmoud.
This is sigma mu, gamma mu, we still have gamma mu there, or, I mean, what's this big matrix? Is it sigma A or what do you
I'm confused. There is gamma mu, of course. It's a spinner.
No, but no, I mean here, in the, yeah.
Gamma mu, right? There are spinners. These are spinners. I'm writing Dirac Lagrangian.
And what's this big matrix?
It's a Pauli matrix.
It's a Pauli matrix. I'm in SU2. We are doing SU2. Of course, if I study SU2, I forget that these guys are spinners.
No, because I imagine that this matrix is 4 by 4, like. And
no, it's here. No, these are commuting spaces. The reason I speak of SU2, it has nothing to do with Lorentz. The symmetry is actually Lorentz times SU2, so I never write Lorentz when I speak of SU2. When I will be doing Lorentz, I'm not going to mention SU2, that I'm going to keep a dummy index. I'm not going to write explicitly gamma mu, so you will go crazy.
I understand now.
Why would you? But the QED also didn't do that, there was just charge there. QED, which I erased, is E psi bar gamma mu Q A mu psi. These are matrices, but I don't write them. Just Q. There is a matrix here which is Q. It's a diagonal matrix whose eigenvalues are 1 plus 1 proton, 0 neutron, or up quark 2/3, down quark minus 1/3. Electron minus 1 and so on. Okay. These are disjoint spaces. So I can always, you know, when I talk of quarks, I forget the color. Unless I study strong interactions. If I study strong interactions, I forget a weak because they are living in different spaces. Okay, that of course you must get used to that. There is a hidden notation here. These are spinners. And so I would write here alpha index if you want it really, okay, just to make. Then I would write like, but you don't want that, right? That'll be too much.
Yes, yes.
You must imagine it.
Yeah, yeah.
Well, the fact that I am answering, it's sort of. There is also the other piece which is Hermitian conjugate. You can convince yourself. That will take a down quark into an up quark. and you will get A1 plus. Notice that I managed to reproduce Wink interaction as long as I decide to call this guy here W plus. Please keep in mind that W plus is made out of minus I. So it happens with our conventions for sigma 2. There is nothing deep here. This was just convention what I call sigma 2. But these are conventions we never change. Good. You see, you must feeling good. You wake up that morning, you plan it, this could work. Unfortunately, well, two things I should say, and this of course becomes a deep problem. If this is to work, these doublets better be left-handed. Weak interactions only deal with the left-handed quark. This will be, I'll talk about chirality as we call it, left and right. But at least the form is good. You can imagine this is actually, I can anticipate it now, this is going to be a problem because weak interactions are left-handed, but photon is funny, or they are funny. Photon is both left and right. This is completely parity conserved. There is left and right here, equally. So you can see that this is going to, because it's going to fail, because if this is left-handed, how will, then this will be left-handed, but photon is not just left-handed. There is even a deeper failure that I'm going to spend a few minutes on.
The first one is photon.
It has to be, I have no choice. If I claim that I have a unified theory, you see, this is how things work. You decide to follow your principle, and then you report what you got. And here there is a deep failure, actually. Who said that? I always forget. We can check together. I think it was Berlioz. The tragedy, a great tragedy of science. So many beautiful theories killed by ugly facts of nature. This looked like a beautiful example of a beautiful theory killed by ugly facts of nature. It saddened me that this didn't work when I learned later. This is why I teach the standard model with this example. You normally never find this in books, so pay attention here. I want to spend some time on this SU2 before going into the standard model. I want you to see the process of getting there. Why? Because I would have to conclude that Q is T3, you agree? Forget parity violation. Even if I ignore that for the moment, Q, I compare, would be E3, and I will conclude that G is E. In my theory, weak and electromagnetic interactions are unified. No surprise. It's one and the same gauge group. So notice weak interactions cannot be weak if you want to unify them. They will have the same coupling constant, basically. Okay? They will look weak because the W boson is heavy. This is what you ask me. This is a fact of nature. That's why they'll end up being weaker, and we'll compare them at low energies only. If I go to sufficiently high energy, who cares that W is mass? Now notice the beauty of this theory. It corresponds to the most amazing thing that I think exists in nature. Quantization of charge. It's crazy. To a precision in 1 in 10 to the 20, charges are quantized. That's mind-boggling. Imagine our masses are being sort of twice as massive as Nicolas, precisely, he twice as massive as Fatma, till 1 in 10 to the 20. That's sort of crazy. How can that be? What is the miracle behind that? You would expect a continuous distribution of charges. And here, by the way, it's continuous. There is nothing to say because this is an arbitrary number in the U1 case. Not in a non-abelian theory. In non-abelian theory, as you know, charges are quantized automatically. This is called quantization of spin. Every spin is an integer times the spin of the electron. Commutation relations, right? The eigenvalues of T3 are integers in the basis of the smallest one, which is a half.
So this time we get...
That's just normalization, okay? Notice that the charges are integers. People talk about fractional charges. Don't get confused. There are no fractional charges. Just call the charge of the down quark 1, and you will see that everything is quantized. The reason we call it 1/3 is what? It was discovered much later. If down quark was discovered before, we would call it charge 1, and electron will have a charge 3. But think of all the charges that you know, right? Dot quark is twice or minus twice the down quark. Electron thrice. Proton thrice. Delta plus 6 times. And so on and so forth. This is predicted here. This is a good theory. Beautiful theory, killed by ugly effects of nature, it seems. Please pay attention to that. I will come back to this issue. This is the first class on building the standard model really today. I will come also on the last class. Why did it fail? Because the eigenvalues are wrong. It's true that it's quantized, but here they would all have the same eigenvalues. Every doublet would have the same eigenvalues. Even if you change the representation, every triplet will have the same eigenvalue. The eigenvalues of SU2 are fixed. But that's not nature. In nature, you have doublets. You know that from this interaction. Okay, 1, U is U, and D is D, quarks. And the charges are 2/3 and -1/3. Okay? And there is another doublet where U is neutrino and D is an electron. Okay, let notation not ever confuse you. Still remember to this day, one of my professors, he was a good professor, when he said, you know, let me write the Newton laws for force. He said, no, this is Einstein law. Someone says, no, he says, E is the force, M is the mass, and this is acceleration. Don't get confused by notation, right? Okay, they are just conventions. So we have leptons here. What are their charges? Unfortunately, they are not 2/3 and 1/3. They are 0 and -1. This can never work. No matter what we do, we can't patch it up. I can worry about how making, parity here broken or broken. Maybe I find a trick, maybe not. But I have to sort of give up. And that's what he did. He gave up. He had a good student who was not completely stupid. Glescher. It was interesting, Glescher did this later when he went to do a postdoc in Copenhagen. He was a student of Schwinger at Harvard. At that time, when he went to Copenhagen, and he decided to take this serious. But before we do that, I want you to appreciate the beauty of the theory that we would not have to worry about the quantization of charge. It will be explained. By the way, this is why some of us like non-abelian gauge series. This is the reason that some of us, or many of us, do grand unification. If you believe in grand unification, that charge will be quantized because you would have, again, the traceless generator. You see, it's coming from tracelessness. The charges cannot be arbitrary. And the commutation relations are tracelessness. So to relate one charge to another. You'll find that in SU3. Look at your neutral generators of SU3. One, for example, is T3. The other is, again, T8, which has 1, 1, -2. Tracelessness. And at the end, maybe it's not so tragic because this failed. But once again, this couldn't have worked because there are strong interactions. this guy who wants to unify or girl interactions at a time cannot be right. You must then add other interactions and put them in a bigger structure, and you'll face the same problem. So even today, we are likely to be wrong, we are unifying, and tomorrow someone may find new interactions, okay, prove us over-ambitious as they always were in the past. Very likely. But sometimes irresistible when the theory is beautiful. Okay. You see, I will be spending some time always in giving you the crux, the principles, the ideas, the physical picture. Okay? Once you get that, you will see. In the standard model, unlike in more complicated theories like gravity, derivations are quite simple. You have just to know rudimentary group theory. You don't need a friend mathematician like Einstein needed Marcel Grossman. Einstein was not so good at math, right? Despite of not being completely stupid, he was not so good at math, so he needed a friend, tensors at that time, if you didn't know them. But the group theory of the standard model is very easy. It's basically a simple. Well, if I don't give up, if I say, well, the beauty of gauge interactions is irresistible, what should I do? What could I do? I want to just go on a little bit and prepare the terrain for Monday when we can actually derive things in the standard model. If you wish, let's say it clearly, this is too predictive. The theory is too predictive for its own good. No, there is a thing. Still, by the way, it's not easy to write a wrong theory. Famous words of Pauli, who had this humor when someone is presenting his or her work, he says that it's not even wrong. Most of the things that you do in life are not even wrong, okay? I'm a little proud. I managed to write a wrong theory once. I even hope that I have the right theory, but we were proven wrong. It was very good. It was a grand universe theory which was predictive enough to be ruled out the way we've written it, following seriously and closely minimality. It gives you a warm feeling. I don't know if you can understand that. I want you to appreciate that, okay? This great thing that Weinberg says, it's amazing that you are writing formulas on pieces of paper, and he's a great physicist, aware of how great he is. And the things that you write on your paper correspond to the laws of nature. It's amazing. You write, and there it comes a prediction. Okay, so if SU2 doesn't work, this is one of those moments when you say, okay, I'll just extend it a little bit. Okay. I would one possible way to go to SU3. Now notice what happens in SU3. The beauty is I maintain the non-abelian structure. That means I will have this thing about quantization of charge. That will be beautiful. We can see how and what. It's of course at some sense minimal and elegant, but it produces a lot of new interactions, because now instead of 3 gauge bosons, there's going to be 5 new more. That means there are going to be new forces, but that may be beautiful.
But
this doesn't work, by the way. It was adapted later by Weinberg himself, SU3, and it didn't work. You would have to add again something else. SU3 won't work. But this is not the direction that Glashow took. He wanted really to be minimal, to add as little as possible, in spite of losing if you wish, the predictivity of charge and the elegance of the theory.
When you use only one group, you say SU3, you will still have also the same coupling constant for all the interactions?
Yeah, of course, in order to have the symmetry, the coupling, well, I didn't write that, but that's obvious. when you write the covariant derivative, unless it's one and the same coupling, you will not preserve that symmetry, okay? That I thought you checked that. We can do that once again. Okay, on Monday I'll remind you of, maybe more systematic, I'll remind you on Wednesday of the group theory of non-abelian. But yes, the coupling constant has to be the same, otherwise it was the symmetry. That's what the symmetry means. You have one, you see, that's what it means. There is one generator, nothing else in SU2, okay, with these fixed charges, there is one coupling constant. Write different coupling constants, you will have 3 U1 groups, but no one SU2. You would lose invariance. It's one and it's real. Hermeticity of the theory makes it real. This is very important. Okay, for example, with gauge interactions, you cannot explain CP violation, just with gauge interactions. We need something more. Nature, CP is violated in nature, okay? This is just a side remark. So this is sort of, this beautiful idea didn't work, was not followed, but it didn't work later on when an attempt was made by Weinberg. Instead, I can just be less ambitious and say, well, but it's sort of, it's kind of painful to do it. It's a little cheat here, but it's minimal. I'm adding just to one. I don't know how to count. I don't know even if it's fair to say, is this more minimal than this? How should we count? There is a danger when we compare different things to minimality. For example, I wouldn't just count particles. This, as Beckman wanted, this has some minimality because there is one and the same gauge coupling constant, there is quantization of charge. There are more particles. Here, for example, there are less particles added, just one gauge boson, but then 2 different coupling constants. I lose the beauty of unification. This is not a unified theory. This coupling constant is called G, this is called G prime. How would the covariant derivative look like now? Minus IGTA and UA. I should have written before, A is 1, 2, 3. It's better late than never. There are 3 generator of SU2 minus I, G prime. The generator of this extra U1 is called Y over 2. Why is it called Y over 2? Don't ask me now. Just the historical reasons to put a half here. I didn't have to do it. And the gauge boson, when you get rid of A's, you put B, okay? This is the glacial theory. Everything is here. Now we can go on and derive the properties on Monday, okay? I'm about to finish. Just to give you enough material to think about on the weekend, I'll write down the thing. The charge here, electromagnetic charge, or Q, maybe I can always specify that this is electromagnetic charge. Sometimes I do, sometimes I don't. I'm talking only of this charge, so it's not necessary. But anyway, to be on the safe side.
Can we go back and don't introduce the new, as you do cross U1, and we say that we will redefine our covariant derivative to be with 2 coupling constants. One with
That's what I'm doing.
So
I don't understand. I have 2 coupling constants.
no, I mean now KA will go only like 2 generators, and
how can I go over 2 generators? There is no group with 2 generators.
no, but
It has 3.
you consider SU2, but with covariant derivative.
But it has 3 generators.
No, you cannot do that.
It has 3 generators. Groups are groups. Groups follow their, Cartan classified them for us. That's what the beautiful thing about groups are. They are very constrained. It's amazing some of group theory. I don't know how much you appreciate it. Okay, to this day, I'm a lover of group theory. Okay, maybe that's my research is based on that. But I fell in love
But I mean,
with group theories from the very beginning, and that's the structure, it's simplicity, elegance. I'm just doing this precisely what you're telling me. However, there are three of them. I can't help it.
But I think because you need to have gauge invariance, you forced to have the same coupling constant for all your generators. This is what I mean. Like,
And once I mention a group, even before gauge invariance, if I talk about global symmetry, there is just one coupling constant. Surely, if I make it a gauge principle, everyone gauge constant. But when I speak of a group, already the language of a group implies one coupling constant. Implies a symmetry between all these three directions, okay? There can be only one. If I say that something has a rotational invariance, that means the force is equally the same in all three directions. The coupling constant of a force, which is rotation invariant, must be the same in z, x, and y directions, or any other, by definition of the statement.
but in that case, you can have like a group which is not completely symmetric, like it's symmetric in two dimensions, but another dimension which is...
Which group you're talking about? We cannot have that. You can't have what you would like to have. You have what you have. SU2, there is U1 and there is a jump to SU2. Then there is a jump to SU3. There is no 5 generator group or 4 generator group, SUN group. Okay, electromagnetic charge must be, by definition, when you write your theory, that means that your charge lives inside the group. That's what you mean by the group. That means that T3 is y over 2. Human electromagnetic, I must add that too. Of course, you may say, why don't you add arbitrary coupling constants here? But this is completely arbitrary, so I don't have to do that. This is a U1 generator, there's no commutation relations. By the way, when I say that groups commute, I mean the following. That they are SU2 cross U1, I'm sorry. That means that the generators commute. SU2 commutes with U1. Has nothing to do with U1. For example, if I have a doublet here, up and down doublet, they must have the same hypercharge. They may not have the same charge because the charge lives in SU2 also, but they must have the same hypercharge by definition. These guys commute. So you cannot give them different hypercharges because then you will screw it up. By the way, what I mean by this relation is the following, that y is 2, q minus 2 is 3. You should read it in this direction. You know the charges and you know T3. You don't know why. And by the way, now I cannot fail. I cannot fail with charges. I may fail with something else. Why? I can't fail because you give me Q and T3 and I'll fix the Y. So this is the sort of, to many people, an ugly aspect of the standard model. Everything else, if you accept that I cannot predict charges, I can accommodate them, but I cannot predict them. I cannot give you charge quantization. I don't know why Y is an integer. I have no idea. Y doesn't commute with anything. So it's arbitrary. Everything else, what I will convince you in the next few weeks, and the rest of the course, everything else will follow in a beautiful, elegant, and simple manner. All you have to assume that there is this arbitrary U1. And then I think we can forgive Gleshow for having to introduce it precisely because everything else will be predicted. Yes?
Now we find the electrical charge in this way, a combination of two different groups. If we want to do the QED, it's like all the QED diagrams with photons, all the interactions that we do perturbatively. We need to include both G and G prime in that calculation of the
No, QED interaction looks like that.
But then Q has T3 and Y.
Q is Q. I don't care about Y. No, I said this is how you should look at this relation. Forget about Y.
Yes, but
You will rederive Y from everything. You don't ever have to think about Y. Never. You don't have to learn it. I, by the way, probably if you ask me, I may know the hypercharges of quarks and leptons. I probably know them. But that's because I've been looking at them for a long time, but otherwise, I advise you don't even, if it's hard to remember them, don't remember them. Please be able to use this quickly, Nicolas.
So the problem for it was that the Q we had in the just considering SU2 was too restrictive for us.
Precise. But it was also predictive because of that.
So,
Here and now, it's not restrictive, but it's not predictive.
so, but on the other hand, we know which are the charges. Of the
Right,
particles.
so we are just...
We can fix to this new.
Right, because we know what the charges are. You see, Gletscher cannot come and tell you, you know, I know what the charges are. Schwinger can tell you, I know what the charges are. They're plus and minus half. Go and look for them. Well, he couldn't say that. He knew it was not true. Neutrino doesn't have a charge plus half. Just look at the neutrino and electron. It's a total failure. Neutrino, in 1957, already existed as a neutral particle. Not just as an imaginary thing that you should respect in weak interactions to conserve
Given
energy.
that this electric charge is the charge of a U1 symmetry, it can be anything. So
That's the, if you look at the QED theory of electromagnetism, then the quantization of charge is a miracle.
it's
By the
amazing
way-
that the,
Huh?
it's amazing that the
It's amazing.
charges are-
By the way, there was one explanation. I don't know if you've heard of that. I can finish the, just to answer your question, Mehmet, is what you really meant that A mu must be some linear combination of A mu 3 and B. We'll rotate them, there will be some mixing angle and so on. But once I do that, I will forget about A3B hypercharge. I will only have to predict there will be another gauge boson which will be orthogonal. If I have two to start with, there will be two of them. That's a famous new neutral gauge boson. The beauty of that, you will see, I'll predict its interactions completely with just one parameter, okay? That makes the theory good. One parameter that can and must explain, you know, tens of different experiments or more. And you can imagine our excitement in the 70s when this started to... I was starting my PhD at the time, and one experiment after another was confirming this, okay? With just one parameter, one simple theory. That's incredible.
So we can express that all coupling constants with
Right. You will see that E is, let me anticipate it, is G sine mixing angle, okay? Tangent theta W, okay, I can just tell you this will come out. I must introduce something, okay, because there are two coupling constants. I call this weak mixing angle, okay? It used to be Weinberg's mixing angle. It's very funny. It was introduced first by Gletscher. And actually, his original paper, please look at the original paper, Weinberg. It's a beautiful paper. Weinberg introduced the Higgs mechanism into the theory that was written before by Gletscher. Maybe I should send this thing for you, because otherwise you'll be lazy to look them up. Whereas Gletscher papers is very hard to read. Weinberg is amazing. He writes original papers, always. And they are immediately like a book. I don't know how, I find it mind-boggling. I've learned most of my physics in I'm a sort of Weinberg type. I like that simplicity and clarity of thought. So I have to introduce some, you see, there is no true unification. This is sort of a mixing between two different gauge groups. Then I predict, notice that the electromagnetic interaction is somewhat weaker than weak. Sin theta W is less than 1. So weak interactions are not weak, okay. Just we'll see again why they thought they were weak. So this is the lecture for today. But if you are not too tired, I wanna chat with you for 2 minutes. Actually, we started a few minutes later. Is that just to see whether you ever heard of that? There was one interesting explanation possible for quantization of charge without non-abelian gauge series, much before 19. I don't know, maybe 40s or late 30s. Dirac writes a beautiful paper, mind-bogglingly beautiful paper. The most beautiful paper of Dirac is not Dirac equation, which is so beautiful. It's a cornerstone of everything we do, right? For us, actually, it's Dirac works, which is the basis, okay? Not so much Einstein's for particle physics. I remember as a little kid, I wanted to break a magnet. It was driving me crazy that you wouldn't have these poles. How is it possible? And my brother, who was 4 years older, would explain to me, no, it cannot be done there, no magnetic poles. But how can that be? It was some 20 years later, I remember when he came home very excited, he says, you know, we were very close, so he didn't have to explain. He says, you were right. There may be magnetic poles. Dirac took an idea, people used to speculate on that. They would say, wouldn't it be nicer if electromagnetism was really symmetric. If you had this duality between electric and magnetic, right? This is my electric thing. There is charge, right? Or density, or I can put a delta function. And then delta times B. Wouldn't it be nicer, says Dirac, if it looked like this? There would be a complete symmetry. It would not be easy to work with, right? Because here I can introduce the A potential, because if the divergence of B is 0, then I can write B as a gradient, and so as the curl of A, right? So we are used to 0 here. He was not first to think about the idea that there could be such magnetic monopoles, we call them. You are in a mood to listen to this for 2 minutes, or you are hungry and tired and fed up? I've been talking these days with my collaborator, one of our diploma students, Vladimir Tejo, from many years ago. It must have been more than 10 years ago, who was my PhD student, actually, an outstanding PhD student, probably the best student I ever had. And when I'm late, he says, no, it's good to be late. I was so happy. People are often happy if the professor is late, he says. And it's very important, don't overdo it, You start hating your teacher who keeps on. He reminds me talking to you. On this side, you're much more enthusiastic than by this, right? Can I go on for a few more minutes? Or you want me, okay? Please, if you're tired, even one of you, stop here. Okay, just chat it. You're not learning anything, okay? So Dirac says, well, let me write the theory of magnetic monopoles. And it turns out, when he wanted to write a quantum mechanical theory of magnetic monopole, and there are wave functions in quantum mechanics, and they have to be single valued. He got an incredible thing. If the time were to permit us do that, at the end of the course, I will spend at least half a lecture, maybe the whole lecture, if you manage, giving you Dirac works from a simpler perspective. And if those are interested, there are many notes. I have some notes I could give you on this, because his paper is not easy to read. There is a Young, same C and Young Wu formulation, simpler. It turns out that what you get, that the product of the electric charge, so imagine all the density, right? Put a delta function. I'm just talking about charges, point charges, times Q magnetic. The product has to be an integer, it turns out. Amazing result, a miracle, okay? Don't ask me why. It's complicated and will take time. So you just need one magnetic monopole. By the way, February 14, 1982, Cabrera, Stanford, thinks he saw a monopole. He's got a little small apparatus, and apparently something like monopole went through this condensator, whatever he had. There was no monopole because much better experiments were looked for at Gran Sasso. There is a laboratory in Gran Sasso Mountains in Apennine, in Italy, above the town of L'Aquila. They had an earthquake. There's a lab there. They have a soccer field size detectors. And there are no magnetic monopoles. So the joke was that there is one magnetic monopole in the universe, went through those plates and disappeared. And charge is quantized, and we'll never know it, okay, because there is one bloody monopole. Okay, I think this is beautiful if there were to exist magnetic monopoles. So this is Dirac. I think this is in the 40s, around 48, I believe. Says that if there is a monopole, then this must be satisfied. One is enough. If you have one monopole, the product of all electric charges must be integers. And vice versa, magnetic charge would also be quantized from this equation. Okay, in some units. This is in 1974 at Hooft, the same at Hooft that is sort of father of the renormalizability of the standard model. I'll teach you what he did, okay, and Polyakov, independently, suggested the following. So if you have a magnetic monopole, you get charge quantization. They said if you have charge quantization, like in SU2, you have charge quantization, they prove that monopoles must exist. So you get charge quantization. And here is the other way around. If you have charge quantization, you get monopoles. And you can imagine that the search for monopoles became a holy grail of particle physics. That I would think would be the most exciting discovery imaginable. Finding things that you understood as a little kid, right, which you eternally look for, become great discoveries. No magnetic monopole was ever seen, unfortunately. So these grand unified theories, that's why at the end I'll have to tell you something. I want to wet your mouths now before we leave. Predict actually magnetic monopoles. Moreover, predict an incredible thing of the fact that you and I decay. And that unfortunately was not seen. So there you go. I found it so exciting I had to work on this for many years. I had my doubts, but I had to work.
Is this something still being worked on? Like when they talk about...
Oh, there are beautiful issues of magnetic monopoles. There are issues you can work on, theoretical issues that are very interesting.
There was something called BPS monopole or electromagnetic...
Yeah, there are all kinds of works. You may get them in extra dimensions. You may get in grand unified theories. You may study their properties in particular regimes and so on. So yes. There is a beautiful review, among others, a very beautiful review by Harvey some years ago, who worked on monopoles. There may be others, okay, this by itself. Unfortunately, it's not as exciting when the experiment failed. It was called the Mutter Experiment. It went on for many years, and he found a fantastic limit. We know today that there are very few monopoles. The flux of the monopoles is less than 10 to the minus 16 per centimeter square per second. This used to be an astrophysical limit called Parker limit, just from knowing magnetic fields, galactic fields, and so on. This became better than the astrophysical limits, okay? We'll stop worrying about charge quantization. In the standard model, there is no charge quantization, there are no monopoles. In the standard models, you wouldn't have these monopoles. You wouldn't predict the existence of monopoles, okay? It will have the SU2 theory like that, or SU3 that Mehmet suggests, or SU5, maybe, whatever, but not SU2 per se. Okay, I took a little more time, but on Monday we can start then. Remember, looking at the predictions, what we'll do, we'll find the predictions for the Z boson. We'll have a homework to study the properties of the Z boson. And then we'll go on and do the symmetry rate.